Okay, shall we continue? Our next speaker is Polina Filippova from High School of Economics, and she will give a talk on algebra of graphs. So you are welcome, please.
Hello, I thank the organizers for giving me the opportunity to give a talk here. I will speak about the hopf algebra of graphs. Here it's written hopf algebras, but actually it will be one hopf algebra. I will not go into too much details, but I will describe the main operations on graphs which we are interested in. Then I will speak about some joins with discrete or empty graphs. There is some terminology issue. And I will describe a hopf subalgebra generated by joins. Then I will speak about primitive elements. And I will speak about generating functions for joins and for their projections. I will define what the projection is. All the graphs form a basis of vectors of an infinite vector space. We will say that a graph is an isomorphism class of finite simple graphs. So there are no loops, no multiple edges, but the graphs may be disconnected. So like this, graphs like this are okay, but we do not consider something like this. And we will take all formal linear combinations of graphs. They form a vector space, and it is graded by the number of vertices. Moreover, there is a structure of an algebra on graphs because we may multiply them. A product of two graphs is just their disjoint union. Note that this multiplication preserves the gradient, because if we take a disjoint union, of two graphs, the result has the number of vertices, which is the sum of their number of vertices. Moreover, there is a co-multiplication. To take this coproduct of a graph, we take all the subsets of the vertex set. Wait, sorry. All the subsets of the vertex set. We take an induced subgraph, and we take a tensor product with an induced subgraph for a complement to this vertex set. For example, we have a path on two vertices. We take an empty subset and do a tensor product with an induced graph for a complement. Then we take a first vertex, the second, and the second vertex, but the result is the same. Sorry. Here, of course, here it's also tensor product. Sorry. And then we take all the vertices as a subset. And these operations turn the vector space of graphs into a bialgebra, and moreover into a hopf algebra. We will denote it also by G. Hopf algebra G. So this is a notion not only for the vector space, but for Hopf algebra too. Now I will speak about graph joins and the subalgebra generated by some graph joins. We are interested in graph joins with discrete graph or an empty graph. So a graph with n vertices and no edges. We take a join. That means that we add the edges between all the any edge of G and between any, we add an edge between any vertex of G and any vertex of this discrete graph. And we obtain, for example, for such a graph with 4 vertices, we obtain such a join. And note that any subgraph of this graph has a similar form. We take all the subgraphs, and it's important here that, of course, k is less than or equal than n. So any subgraph has a form hk when h is a subgraph, maybe it's the G itself, and k is less than or equal than n. Next, it follows from that all such graphs generate a Hopf algebra. And for example, if we take again a path on 3 vertices, the corresponding Hopf algebra will be generated by the graphs of such forms, of such graphs. We just take all subgraphs of this path on 3 vertices. Now we'll speak about a very important subspace in this Hopf algebra, a subspace of primitive elements. We call an element primitive if the result of the co-multiplication is presented. Note that unit is not primitive, but I will not it's an easy exercise that unit is not primitive. These 2 graphs are not primitive too. We may just write their co-product and see that this co-product does not have this form, but we may take their difference. If we take the difference, this will cancel out, and the result will have such a form. So their difference is a primitive element in the Hopf algebra of graphs. There is a construction that allows to obtain more primitive elements using the similar technique. But first, it's important to know that Milner-Moore theorem states that some graded bialgebras are isomorphic to the polynomial by algebra generated by primitive elements. And in our case, the conditions of this theorem hold. We just state that we work on the fields onto the fields of characteristic 0. And our bialgebra is connected because G0 is generated by one graph, so it is isomorphic to the field. It follows that there is a projection onto the space of primitive elements along the subspace of decomposable elements. It has such a form. We take all the partitions into subsets of the vertex set, and we take the product, that is a disjoint union, of all induced subgraphs with such coefficients. This sum is finite because the number of vertices is finite. For example, for the path on 3 vertices, we take 3 partitions here and 1 partition here. Here are the partitions into 2 parts. And here is a partition into 3 parts. So it works like this. Why we are interested in projections in primitive element? One of the reasons is that some graph invariants simplify when we take it on projections. There are more graph invariants that simplify, but I don't have the time to define them and to speak about them, so I will say some words about chromatic polynomial. I will note that the chromatic polynomial is a number of proper colorings. Into C colors. It turns out that if we take a chromatic polynomial on the projection, on the primitive element, it's always linear. And for example, we take this path on 3 vertices. Its chromatic polynomial is not linear, it's a polynomial, but when we take its projection, it's easy to check that it's just a linear part. And there are other invariants that simplifies, and it's an important reason because we want to know more about primitive elements and about computing them. It's much more convenient to work with such joins. We are interested in projections of joins. In particular, if we collect the joins with graphs with 0, 1, 2, and so on vertices in one generating functions. So this generating function is of such a form. Note that the power of x in each summand equals the number of vertices in the corresponding graph Gn. V of G plus n is the number of vertices of graph Gn. Now we obtain a generating function for projection by substituting projection P instead of instead of Gn. Now, for example, if G is a cycle of 5 vertices, we just take this graph joined with 1 vertex, with 2 vertices, and so on. Then it's sometimes if we want to work with generating function for projections, we need to compute the projections for a big number of graphs. But I want to present a theorem which simplifies the process of computing the generating functions for projections of such joins. We denote by K1 the graph with 1 vertex and of course no edges, because there is a convention that there are no edges, just like this. And know that the structure of this generating function is similar to the structure of the projection, but we have an exponent here. We take again a partition of vertex set into K subsets. We have the same coefficients. We take the induced subgraphs, but here such an exponent is added. I will remind that the formula for projections was like this. This is the formula for projection, and this is the formula for the generating function. So this is the main result, and it simplifies the process of computations, and maybe it has some other application, but which we don't know yet. Oh yes, I will. This is some. So we spoke about the structure of hopf algebra and about the primitive elements, and presented a formula which allows to compute, to make computation easier, and has much in common with the formula for the projections. This is some literature. This formula is to appear in the first paper. Thank you for your attention.
Thank you, Polina, for this very nice talk. Are there any questions to Polina?
Sorry, Elena, I have not a question, but a comment.
Yeah, sure, Sergey, of course.
If I am allowed. Polina has not mentioned, but she has applications of this formula, in fact, because the formula allows one to compute explicitly certain graph invariants. Which are rather complicated to compute directly, but they can be computed by means of this formula for a series for a certain series of graphs, and we can investigate these values very efficiently.
I see. Well, actually, Polina mentioned about chromatic polynomial, right?
Yes, it was a first example.
Right, but you also said that it is possible to consider this approach for another kind of graph invariance. Which kind of, which type of graph invariance could be considered?
There are some graph invariants connected with chord diagrams. So we want to construct a graph invariant. We want to know if there is a graph invariant which coincides with the weight system SL2 for chord diagrams on intersection graphs of some chord diagrams. These graphs these graphs are not intersection graphs, but using this formula we obtained that some values for this invariant if it exists.
I see.
So
could I ask some questions?
Oh yeah, sure, Alexander. Yeah, please.
So we are looking for this main result. It remembers me something familiar from the combinatorics of graphs when we calculate the number of all graphs with a particular property and the number of connected graphs with the same property. There is usually a logarithmic law how to relate generating function for this. I think this is expression is very similar from those coming from this exponential law. Roughly speaking, we have to find some logarithmic function among these calculations. No, of course, maybe this is for Sergei Landau question. Would we recognize something similar in this well-known logarithmic law between all sub-objects and objects which are connected?
Sasha, you are absolutely correct. And this logarithmic law works, in fact, perfectly in all graded commutative, co-commutative hopf algebras, as Polina has mentioned.
Yeah.
And indeed, primitive elements are those that generate the hopf algebra of graphs. So it's nothing strange that the projection to primitives is the logarithm, and it is the logarithm of the identity mapping. The logarithm is understood in the sense of convolution product.
Yeah, something like that.
Yeah, and Polina's result is an extension of this logarithmic law to the exponential generating function for some specific, certain specific families of graphs. Those families that are obtained from a given graph by joining with discrete graphs.
Yeah.
Also, I'm interested in this formula where we have a cone over graph, cone with 2 points over graph, and so on.
Right.
Just recently, we investigate some invariants related with graph, namely so-called Jacobian for graphs, and also investigate the structure of Jacobian for cone over graphs. There is a very nice relation between, but in general, the Jacobian for cone is more simple than the same invariant for original graph. And also cone over graphs in many cases related with some invariants coming from the knot theory, namely invariants which are obtained in the investigation of cyclic branch covering of knots. So it's, for me, probably not so surprising, but it's just pleasure to see that this cone structure also appeared in this sequence. Wow.
I see.
Just some comment.
I see. Okay, thank you. Thank you very much, Alexander, for your comments. Yeah, every time it is interesting to find some relationships between new results and some other results which were obtained or known in other areas, right? You mentioned that some similar results were obtained in knot series. That is interesting. Well, okay, are there any other questions to Polina? Well, if not, then let us thank Polina again. Thank you very much. It was very nice, interesting talk.